8 Master Black Belts. What we're going to talk to in this video is the full factor design of experiments for 4 factors. If you're new to design of experiments, I suggest right now to go back and review the prior 2 DOE training sessions. They are out on my website, and you'll see the reference to the website at the end of this video. If you have reviewed them and understand them fully, then fine, let's go on to this one. This one is, one more time, is a 4-factor full factorial DOE. There is several ways that you can put a 4th factor into the design process and to the implementation process. There's several good books on it, and we will also talk in further videos on how to do it with what's called a half factorial methodology, which is a very popular way of doing it. What we're going to do this time is we're going to do a full factorial, do it as a full factorial. It's going to take longer, it's going to take more runs to do than if it was a half factorial, but it gives you a whole lot of useful information coming out of it. So let's get into this tutorial. Once again, if you're new to design of experiments, at this particular point, I would strongly suggest start implementing them either in your place of business, and these can be done in a very short period of time, anywhere from 2 days to 4 days, or you can also do them outside of work. And there's been plenty of articles written on how to do this with engines and with cars and different types of machinery and so forth that are right around the house. But let's go to the next step and let's understand how to do a 4-factor full factorial DOE. Okay, let's get into it. The final phase what we're going to look to is going to be described on the board, on the whiteboard behind me. And basically, if you remember from the first 2 videos in this area, we've got 2 cube plots. Now we're going to get to this. This will be the final phase, but I want to show everyone what we're eventually going to get to through the DOE process. But let's look at the complete design of it. And let's start with our original design that we had. And this was actually one experiment that was done back approximately 5 years ago at a chemical plant. And what we have here is we have a cleaning tank, and we have a defect that's coming off of there. Defect is running with about 20% of the material coming off it, and the defect is a yellowing process or a dirty filming process on a strip of metal that is dumped into the tank. The 20% that comes off of there goes through a rework process and must have a complete cleaning operation by hand. So it is a very problem area, a very costly problem area to this this manufacturing process. One in this particular case wasn't making very much money. So what do we have? Well, we assembled the operators, assembled the subject matter experts, and we also put the green belt or black belt on it, and in this case it was myself. And we assembled a team, and we looked at all the variables that could potentially affect it. And in this particular case, we originally looked at it, when we did it the first time through, we looked at it in terms of the concentration, or the percent on it, the pH level, which was primarily driven by the type of water that was being used in the process, the temperature. There was actually a heating element inside the process, so you could regulate the actual temperature that it was cleaned at. And we originally looked at those 3 variables, the pH, the concentration, the temperature. Well, what we're going to do this time is what we actually did when we did the DOE on this, is that we took the temperature, the pH, the concentration, and we added the 4th factor into it. In this particular case, it was the 4th factor was the time. And the time was how long it was left in the bath. Now I'm going to review some of the highlights of what occurred in this process, and this is a review of the DOE from 2 videos ago. And we took the concentration, and again we went through the same process that was explained in that video. We assembled a design team. What's the farthest you've ever ran the process? Let's move it to the extreme. What's the lowest end you've ever moved it? Well, let's move it to the other end. We're not going to destroy the equipment, but we want it to move far enough out so that we can understand the process and we can understand what potentially is driving the process, at least on first phase of the DOE. So what we've got through here, through the team development, We have the concentration. We move the concentration from 20% on the low level, and we will call that the minus, up to 30% on the high level. We took the pH from a 6 up to pH of an 8, and we took the temperature from 140 to 160. And the 160 was the maximum level that we could get on the equipment. The 140 level was, as an example, was the lowest that they would feel we could get to without freezing the tank up. This particular time, though, is we adjusted the time. We took the time from 20 seconds to 40 seconds as the fourth variable. Last time we did this, this was one of those variables that we held constant all the way through this. So what we did is we took those variables that we felt had very little influence on the process, and we held those constant all the way through the process. But in this particular time, we said, now wait a minute, that time may be a critical factor in this whole thing. And by the subject matter expert, we decided to add that one in. Well, there's a magic little formula that you can do off of it. When you have 4 factors at 2 particular runs, you take the high-low and the low-low, the 2 levels that you're going to, and the number of factors, and you take the 2 levels and raise it to the number of factors level, or 2 to the 4th, and you come up with 16 runs for a complete full factorial DOE, as what was done in this particular example, and what we're going to walk through for this particular example as well. So let's go over to the design on the other side and look at very basically how it was set up and how it was done, and then we'll switch over to the analysis of the cube plots. We originally set this up with 8 runs with just the 3 factors. The 3 factors being the concentration, the pH, and the temperature. And if you remember from the prior videos, we took the concentration and went minus, plus, minus, plus, minus, plus, minus, plus. The minus and the plus correspond to the low level and the high level that we used and we developed from the team development and the design team on it. And that was for the concentration. For the pH, we moved it from, we found the pattern of 2 minuses, followed by 2 pluses, followed by 2 minuses, followed by 2 pluses. Very simply, the minus was a 6, and the plus was an 8. The temperature, when we did it the first time, we had the first 4, followed by the last 4, the first 4 were 140, followed by the last 4 for 160. We took all those 8 runs, this is how we designed it, and then we randomized the 8 runs and ran the particular 8 runs through the design, which took about 8 hours to do. Well, what we actually did is we came back and said, well, you know, when we go to run it, actually there is that 4th variable, so let's add the 4th variable in there. One more time, the 4th variable is how long we left it in there. The time goes from 20 seconds to 40 seconds. And all we do is add it into a 4th column, and we take and we put 8 negatives, corresponding to the 20, followed by 8 positive, corresponding to the 40. Very simply, and then we take this entire pattern that we developed for the first 8 and duplicate it for runs 9 through 16. So when we do this, we basically have what's called a full factorial. We'll show it on the cube plots coming up next and how we analyze the cube plots. And if we understand the basics of understanding the cube plots from the prior videos on 3 factors, this one is not a whole lot different than the analysis done there. What is interesting on this process is that with a full factorial is that we can get a complete understanding of potential interactions between any pair of these, between the concentration and the pH, or the pH and the temperature, or the time and the temperature. We can also understand any of the potential main effects, such as the concentration by itself, or the temperature by itself. We can also understand the 3-way interactions, and the 3-way interactions might be the pH, the temperature, and the time, all acting in agreement with one another, such that when we have them all at one particular level, that's when we're able to eliminate the defect. And it also has one big effect to it by doing it as a full factorial, is that you can take the concentration, the pH, the temperature, and the time, and if all four of them together are needed to be at a certain level to eliminate the defect, this design and this DOE will actually find that four-level combination. Further DOEs we're going to talk about, getting into half factorials, will not pick up what are called four-way interactions with four variables. So this is as an added bonus behind doing it. Yeah, you got to sacrifice a little bit. What's the sacrifice to it? Well, you're going to have to run 16 runs. And if the material is there, and if the time is available on the actual equipment, and this is a very, very strong DOE to do, one that I've used several times. The four-way interaction between the concentration, pH, temperature, and time, a lot of times those show up as being what I call gold mines. And because, quite frankly, they couldn't have been found any other way other than through the DOE process. If you think of some very famous four-way interactions, the internal combustion engine is basically a four-way interaction between the carbon content, the oxygen level, the pressure, and the heat requirement for it. You put all those four together at the same right concentrations, and you're going to an explosion off of it, and that turns into the internal combustion engine. So one more time, what we're going to do is we're going to take the process, and all we do is the same as we did on the prior videos. We take the time, concentration, pH, and temperature. We added, instead of 3, we have 4 variables now, and we do it off of 16 runs. And we found the very basic same pattern that we did originally, except we add the 4th one down, and we put 8 negatives, followed by 8 positives. And then we take the first 8 runs, and we duplicate it down below for runs number 9 through 16. And every combination potential off of the 4 variables is covered. Okay, now what we've done is we've ran the 16 runs, and that may have taken 8 hours, that may have taken 12 hours to do this. Strongly recommend you not doing it over multiple number of days, as you may have an environmental factor that may come into play, or some other factors such as raw materials, changes in crews, and things like that that are occurring. So with those changes in factors that sometimes you cannot avoid, the idea, as we showed on one of the prior videos, was to reduce the variation off the process, and to do that over as short a period as possible. So let's proceed on as if we did these 16 runs over an 8-hour period, or a short period of time. When we first did the 3-factor 8-run DOE, we actually did it with 1 cube. And again, this is the picture of the cube. We have the picture of the cube with the concentration at the lower level, with the minus going to the plus, and the pH going from a minus to a plus along the y-axis, and along the z-axis being the temperature going from a minus to a plus. If this was a 3-level full factorial, we are looking at 1 cube plot. When we add the 4th variable onto it, we are looking at a 2nd cube added onto the analysis, onto the view of it. When we do that, the time is now going to be the other factor. We go from a time negative to a time positive. And so time negative is over here, and time positive is the additional cube on the right-hand side. With this, every corner of each one of the cubes is represented by one of the runs. And as an example, for run number 1 of the design, the concentration was at a negative, the pH was at a negative, temperature was at a negative, and the time was at a negative corresponding to that particular point. And the opposite side would be all positives, which would be the upper right-hand corner, which corresponds to the temperature positive, concentration positive, pH positive, and my temperature positive over on the positive cube. There is several analytical methods to analyzing 4 factorial DOEs, and we went through how to analyze the longhand methodology and the mathematical methodology for a 3-factor 8-run DOE on the last 2 videos ago. This one, what we're going to do is that the analytical method is almost identical to what it was on the full factorial for the 3 factors. What we're going to do now is we're going to do this by a graphical method to understand what is potentially where our factors are coming from. So let's go through a list of potential factors that could and where they would show up after we graph them. Let's go first off of a main effect factor, where that would show up at. What we're going to do is we're going to plot off with a dot or a bubble plot the defect, and we're going to show the defect in red. In this particular case, it was that yellowing or that dirtish film that came off there from not getting totally cleaned. And let's take, for instance, that when we did this and we analyzed them all, that our defects showed up on all corners of that cube and that cube by itself. Well, I think everybody can see that one. That one is pretty obvious at that particular point, that it all is related to the particular time. And that when I went from a time negative to a time positive, and we went from 20 seconds to 40 seconds, that when we extended the time out, that is where we ended up with the defect, and that's where it was caused by. Now, those happen, and those happen some particular time. They are probably, in most DOEs, going to be rare that you get a main effect and a main effect acting by itself off of it. The reason being it's probably not going to happen during most DOEs is because most people, most processes can see DOE, can see main effects pretty easily, and the operators can pick them up pretty easily. The human brain has a real strong ability to pick up main effects. So those probably are not going to be there. They might be, and if you do, fantastic. All right, that's going to be one of your critical factors. So let's go through some options that are probably going to be more likely they're going to come out of the DOE that you didn't have before. And let's say that the defect level was in 4 locations. And it showed up in most 4. Well, what do we have going on with those 4 when we do that? Well, the defect shows up when we have the concentration at the high level and the pH at the high level. When we have those 2 together, which is those 2 runs and those 2 runs, which is a common factor throughout them, we have a 2-way interaction going on between the pH and the concentration. Those again can show up on a 16 run. They can show up on your 8 run. It would have shown up if you did it with 3 factors only, without the time, and they would have showed up in this upper corner. But now you've got double confirmation. Basically, you've got it as with the time at positive as well. Notice that with this finding off of it, that you have a couple factors that probably didn't come into play off of it. Number 1 being the time. Your time when you went from a negative to a positive, the time still showed up with the defects, and the defects at the pH of plus and a concentration of plus. So the time was not a factor off of it. And the way I drew it up here, the temperature off of it was probably a non-factor too, as the temperature went from a negative here to a positive here, we still had the defect, and the temperature went from a negative to a positive here, we still had the defect coming off of it. So that's a classic 2-way interaction that can be found off of a 16-run DOE. Let's go over one more classic DOE that you can pick off the graphs. Again, you can pick this up by the mathematics off the process, and you follow the same procedure as it was done when we reviewed it on the two explanations ago. But let's take, and let's do one more, and let's say that the defect showed up in the back corners, the back of the cubes, and the upper planes of the cube. Well, what is common if we had the defects at those particular points? Well, what is common between those two is that the temperature was at the high level and the pH was at the high level. Temperature was at the high level and pH was at the high level on those two and on those two. Again, classic two-way interaction. For whatever reason, those two, when you put the pH together in connection with the high temperature, that was given the defect. Two-way interactions are very, very common findings in design of experiments. If the process is running very, very inconsistent, it is likely that it's probably coming from some sort of two-way interaction. Well, why do we make those statements? Well, let's talk to where it was probably running all along anyways. It probably had a setting that allowed the temperature to fluctuate between 140 to 160, and the pH to float all over the place within a set boundary. And when those two combinations came up to at their high ends of their scales together, that's when you ran into, or we ran into, a high series of defects and high series of defects coming out of the process. So again, the two-way interaction is probably one of the biggest finds coming off of the DOE process. Much more likely to be a find than you will if you do it with just the main effects as we did prior coming off of it. That's a two-way interaction. Now there's various other two-way interactions in the entire process. You can get two-way interactions between any two combinations of them. You can get a two-way interaction between time and temperature, time pH, time concentration, pH concentration. There is, I believe if we go off of it, I think there's 10 combinations off of it that correspond to the potential interactions. Best way to find them, plot them out and look at your Q-plot, especially on the very basic level ones that are done with attribute data, yes-no type data. A lot of times ordinal type data is very good at this methodology, and we've also done it with variable data, although variable data you can do it with the mathematics quite easily as well. So let's go to the next one, and the next one is the three-way interaction, and talk to the three-way interaction. Let's say that we had a three-way interaction between the pH, the concentration, and the temperature, but not the particular time. And let's say that they were all three of them were at a positive level, and when they were all at the elevated high level, this is what might happen. And you get the defect at a pH positive, a concentration positive, a temperature positive, and a time negative, and the same three combination over on our right-hand cube with the temperature positive in the upper right-hand corner. Classic three-way interaction. It took all three of them together, and that was causing the defect. And it shows up in, as being independent of the time factor. And if time was a factor in how much productivity came out of this operation, that's probably really good news in this operation, because we would not require any adjustment potentially with the time, and that we could run it as fast or as slow as we wanted to run it to maximize the flow going through the process. But to eliminate the defect, all we do is, now in a particular case, is to reverse the process and eliminate one of those three, or eliminate those three from happening together. We can also, if these are costly factors that is where it's happening at, we can now reduce the cost of the operation by reducing the temperature off of it and making sure we never run at the high end of the temperature scale, and such things like that. And those are the follow-up operations that come off of it. The final one coming off of it, that you can pick up off of it, and it's rare, but as I talked in the introduction, they do happen. And that would be where the defect only shows up in one location. In this particular case, let's say that the pH was positive, the concentration was positive, and the temperature positive, and the time was negative, such that we were running extremely fast. That would show up as a defect. That would be a classic four-way interaction. Now, four-way interactions are normally rare. So the first reaction you have in this is to recheck the material to make sure the material is correct. It wasn't mislabeled, misclassified, or looked at by someone else in the process, and make sure it's consistent. The second thing is to immediately come back the following day and run what's called a confirmation run off of it to make certain that it is correct, as if you would do with all various outcomes of this. But this one would be a classic one. Recheck everything off of it to make sure it's correct. Okay, so what do we have covered here? Well, we went through the whole development of the process. We went through the development of the entire four-way development of it, the 16 runs. The Q plots will tell you which direction to go into. The mathematics will tell you as well, but very quickly and very easily, the Q plots will tell you what direction to go in. And when you're doing these out on the factory floor, or in certain other processes that are non-factory related, this is a very quick and very fast area to get quick results and to understand the process and to understand where to go next. Now again, one more time, this is going to take 16 runs to do this complete analysis, so don't be surprised if this one is probably going to take you a couple days. If that's the case, proceed with caution. But what we're going to do in another video coming up will be called the half factorial, and understand how we can do the same analysis and get very similar results, although not completely as good as this results are, with half the number of runs, and basically do it off of 8 runs. That will be coming up in probably the month of coming up in future videos coming up. This concludes the DOE analysis for adding the fourth factor in. The follow-up videos coming off these will be the analysis of the half factorials and what to do when there is 5, 6, 7, or 8 factorials, or factors, and quite commonly called screening experiments, and how you design those and how you run those. Once again, I hope you all try it and implement it. The whole secret to design experiments is not in the design and not in the analysis, it's in the actual doing. And the more you do it, and the more you get practice you have at it, the much better you're going to get at it, and the less stressful and much easier to do, and the more successful you'll have at it. Thank you.